ANOVAs don't just work on their own. You have to do one more step if you end up with a significant result. Today we're going to talk about a post hoc test. You are going to learn how to use Tukey's honestly significant difference from start to finish using Python. I'm Jacob, and I am a human factors consultant. In order to show you Tukey's honestly significant difference, or Tukeys HSD, we're going to show you how to implement the F distribution, the studentized range distribution, the Oneway ANOVA, and all the code that goes along with those. If you want more details on how each of those are implemented, we've done videos on each of those topics. So in this video, we're going to show all of the code, but we're not going to go into details about how that code works or why it works. So we're starting off with our imports. We're going to do math, scipy.integrate, decimal, CSV, and random. We're going to set the precision of decimal to 100 significant figures. To start ourselves off, we're going to implement our own version of gamma. So we've used the gamma function in several videos before, but we've always done math.gamma. So to do this, we're going to just take one argument and then we're going to do a nested function. What this function is called is not important. We'll just call it function, and I'll take two arguments, t and z. Next, we'll define a constant, e. This is Euler's number. Just do math.e. This is approximate equal to 2.71828. If you want better precision, you can, math.e gives plenty of precision. So now we've got to put everything in decimal. So I'm going to just copy the decimal part of it and then paste that. So we do t to the power of z minus the decimal of 1 times decimal of e to the power of negative t. And we'll put all of this in a return statement. And then the next part will be to just integrate this, and then we'll return what we get from the result of integrating it. The reason we are doing this is so we can handle some bigger numbers being put into the gamma function. It's one of our bottlenecks. Some of the bottlenecks like this we can do something about, some of them, others we can do something about, but take a lot more time than what is warranted for this circumstance. If there's an interest in going into more of that, we can do that down the line. Other places, we'll just have to throttle the degrees of freedom that we can use because computers don't like titanically sized numbers. And I'll point that out when that happens. So now we're just running a quick test. So gamma 2 should give us about 1, gamma 3 should give us about 2, and so that shows us that the gamma function works to a decent number of significant figures. Next, we'll just speed through our F probability distribution function. So the top part of the numerator, the bottom part of the numerator, and then the numerator itself is the top and bottom divided by this top divided by the bottom taken to the square root. And then the denominator is the beta function times f. The beta function is gamma a times gamma b with gamma a plus b. And then that will lead us to doing our p-value. To do this, we will need to integrate our F distribution PDF. To do that, we will go ahead and just integrate it using scipy.integrate, similar to what we did for the gamma function. Again, we've done this in a previous video. Rather than doing the cumulative distribution function, we're just doing the integral of the probability density function. This is mostly done for conceptual simplicity. You can do the CDF just fine. So, and again, we're just going to return P from that. And we're going to go ahead and run a quick test. We should get something around 0.1 if we feed in like 2.5, 2, and 30. I remember from our previous videos, I'll run that real quick. We got 0.0. That is not correct for what we put in. So let's go ahead and run down where we got the typo. Now, if this is your first time, if you haven't watched the F distribution video, you might not catch this, but we multiplied rather than added. So let's go ahead and fix that and run one more time. And we got 0.9. So 1 minus 0.9 will give us 0.1, or at least really close to it. Yep, 0.9. All right. So that works. Let's go ahead and move on. Now we're just going to stuff in a quick function that will get a mean. We've used this numerous times. It's the same as every other video we've used. So now that we have that in place, now we actually have to calculate our F. So we're going to take a little bit of time to go over some of the differences here because we're actually going to switch from using lists to using dictionaries. So the reason that I've been sticking with using lists so far is because they're very simple and straightforward to work with. Not that dictionaries are hard or anything, but for somebody that's not familiar with Python, a dictionary might come across as a little bit overwhelming the first time you see it. So a dictionary basically follows the format of where you define it with the curly braces, and then it has a key that is a string, and then it has data after a colon. And then you have another key that is another string, and then you have more data after a colon, and so on. That data can be a list, it can be another string, it can be a number, it can be whatever you want. It can even be another dictionary. So the format we're going to follow is a key and then a list. And this will be important for Tukeys HSD because it'll allow us to keep track of the names of the levels of our factor. So we've defined an empty list, called it means. Now, this is one of the first major differences. So rather than just doing the length of our factor, we have to do group size. Group size will be the length of next iter factor dot values. And then to loop through this is our next big difference. So for level and values in factor dot items, that will give us the list that is in each part of our dictionary. Another thing to keep in mind with dictionaries is that they are not ordered. Every time you loop through it, it'll spit things out in a different order. You can do a ordered dict from the collections import, but it doesn't really matter in our case. We're not going to bother with it. So then we're just going to get a mean from values and then append that to our means list. Then we'll use that to get our overall mean. In our example coming up, we'll show how to write out a dictionary as well. So now we're going to go ahead and calculate our between groups sum of squares. And again, other than these changes, this is all the same as in our previous video. So we're going to start speeding through some of this. We're going to start in on the between groups sum of squares. Go ahead and add ourselves a little bit more space and continue speeding through this. We're just putting together all the elements that we covered in our video that went over doing the Oneway ANOVA. So that gives us our first part of our F ratio. Now we go to the within parts of our F ratio, the within groups part of our F ratio. Take note, we're looping through a dictionary again. Before we didn't really need to worry about it for the part just above. So we do for level values in factor.items, and then for value in values, because we're referencing the list inside each factor. And we get the deviation score, we get the mean, we get the deviation score, and so on. Other than that, it's basically the same. The within groups part done. That gives us the second part of our F ratio, so we can go ahead and do an F ratio and return that. So we're going to make ourselves some more space again, and then start in on the Oneway ANOVA. So this is going to have the same exact differences as the F distribution. We are using dictionaries instead of lists, but because we've already talked about that, we're just going to head and speed through this because we've already gone through how to do the Oneway ANOVA. If you have any trouble here, you can also reference the Github. The file will be uploaded by the time you're watching this video. Also note that we are doing a shortcut with our degrees of freedom. Again, this is just because dealing with really, really big numbers is a bit of a chore, and this is a way around it. So we're going to go ahead and get through the rest of that, then return our p value, our f value, whether or not it's significant, the degrees of freedom between and degrees of freedom within. With all that, we'll make ourselves a little bit more space, and now we can finally do the Tukeys HSD. To start in on that, we're going to have to do the studentized range distribution again. Like we did last week, we're going to have to get our standard normal distribution PDF and CDF. We've gone over this in the last video, and then we also did a video dedicated on just the standard normal distribution. If you want more details on those, you can go back and reference those. We're doing a shorter function here than we did there. So it's going to look a little bit different, but it's the same mathematically. And then rather than taking the integral of the PDF, we are just going to do the CDF, which is, again, the same thing. With all of that in place, we are now set up to do the studentized range distribution CDF, the cumulative distribution function. We don't have to take the integral of it to be able to get a p-value. This function itself will give us a p-value. And just like our last video, it'll take 3 arguments, and this is all exactly the same as before. We're going to go ahead and just speed through this and then check our work to make sure everything's okay. We're also going to put in a check for the degrees of freedom, because if If our degrees of freedom are too big, this just gets really unhappy really fast, and we don't really have the time to deal with it in this video. We're already building on a lot of our previous content. We're trying to speed through it as fast as we can, but there still is a lot to go through. So as we're getting ready to actually go over the calculating Q for Tukeys HSD, I want to talk about what's important about it. So essentially, Tukeys HSD is a t-test that adjusts for family-wise error. So family-wise error is the sciencey term for if you throw enough statistics at a wall, some of them will stick. If you just keep on throwing stuff, eventually something will turn up significant. And what Tukeys HSD does is say, wait a second, we need to kind of take into account that we're throwing a whole bunch of stuff out there at once, and we need to be a bit more conservative about what we value. So Q is always going to be the positive difference between two means within a collection of means, and that is always going to be divided by the standard error of those means. And again, we're going to start off by using our number of groups, which will just be the length of our factor. That's the same as when we're using our list, but the group size is using that dictionary format. So length, next, iter, factor, dot values. So now we're going to define means, which will be a dictionary. We need to do this so we can keep track of the names of our levels of our variables. And then we'll go ahead and loop through each level and get the list of values associated with that. To do that, we do for level values and factor dot items. Then we'd get the mean of that, and then we go ahead and build that into a list. So that will give us the mean and the name of the factor that it goes with. That way we can keep track of this all the way through. And again, this is the same format: key, data. The key is a string, the data is, in this situation, another list. So with that, we can go ahead and calculate our within groups sum of squares. This is basically the same as above with calculating the F. We can actually just go ahead and, as we're typing this out, take a quick look up above and compare, and we'll see that these are the same thing. So we go up, take a look, we see calculating deviation score is the same, how we do it, that's the same, everything's the same. So we'll just rush through the rest of this. It's also important to note that this assumes that all of the groups are the same size. If it's not, we need to do something different. It's called the Tukey-Kramer method. So for this, there's a few different ways we can calculate Tukeys HSD. They're all mathematically the same, but you'll see a couple different formulas wandering around. So for this, we are going to just do the denominator is going to be the within groups mean squared divided by the group size, and that will take the square root of that. So with that, we'll go ahead and make an empty dictionary, call it Q's, and then we will loop through our means. So we'll do for mean value in means.items. And then we'll do for other values, so other mean, other values in means.items. And then we'll say if the value is not equal to the other values, then we'll skip it. With that in place, we can now go ahead and calculate our Q value. So we'll say Q equals, we'll round this to 4 decimal places, the absolute value of our value minus our other value. And that will be divided by the denominator we calculated above. So that gives us our Q. Again, we'll round that to 4 decimal places. And then we'll say if the Q, or if Q is not in our Q's, the values for our Q's, then we'll go ahead and make the key. The key will be the mean plus space by space other. So this will say, such and such by such and such. Then we'll say that key is equal to the Q rounded to 4 decimal places. And then we'll return our dictionary that we just built. And with that, we'll go ahead and make a little bit more space and start in on the Tukeys HSD test itself. This will take 2 arguments. It'll take our factor and our alpha. And then we will start off by getting our Q's. And we'll do this, we'll make a dictionary and we'll call it Q's equals, calculate Q's factor. Then we'll calculate our group size. And this is length, next, iter, factor, dot values. Then we'll go ahead and get the number of groups, which is just the length of our factor. That'll give us how many keys there are in our dictionary. For that, we can calculate our degrees of freedom, and to do that, we'll just take our number of groups and multiply it by our group size minus 1. Then, because again, computers don't like really big numbers, we'll just say if our degrees of freedom is greater than 349, our degrees of freedom equals 349. Next, we'll go ahead and define significant queues as a empty dictionary, and then we will go through and evaluate if each of the queues we have is significant. So we'll go ahead and say for key value in queues.items to loop through. And then for each of those, we will go ahead and get the p value. And we'll pass in value, number of groups, and degrees of freedom. Then we'll say if p is greater than or equal to 1 minus our alpha. We'll then take the key, the value, and the p that we just calculated and add it into our dictionary. So we'll say our significant queues for that key is equal to a list that is our p-value. We'll go ahead and round that to, or 1 minus our p-value. We'll go and round that 4 decimal places and then put in the q. That way we can see the q value at the end. And with that, we'll return our significant queues, and that is our main Tukeys HSD. We'll go ahead and make ourselves some more space, and that is our, that is all of the stuff, all the code we needed. So now we can go ahead and start in on an example using this. So we're actually going to continue using dictionaries. So we actually have to build a dictionary of our data. Let's off by doing full race factor. And we'll go ahead and type out the first one and then speed through the rest of them. So white, string, that's the label, colon, then an empty list. Black, colon, empty list. American Indian, colon, empty list. And we'll keep this on. Then we'll do the same for the other 9 variables in our data set. Again, we're getting this data set from IPUMS. It's also in the GitHub. We go over this data set extensively in previous videos. We're gonna go ahead and open it up. Again, this is the same as we've done in previous videos for our filtering. And then we'll be adding it to the appropriate part of our dictionary. If you'd like a little bit more detail on how this is done, you can see back in some of our earlier videos how we do this. So once we have all this, we can start filtering into each race category. So we'll say if int row2, which is our race variable, equals 1, we'll say full race factor white, which is the key we're referencing, which will then access that list, and then we'll append the income for that entry. Then we'll say elif int row2 equals 2 to look at African American. We'll say full race factor black dot append int row 6. Now, for the sake of saving time, we're going to go ahead and copy and paste these, change the name of the key, and then change which number we're looking at, which number code we're looking at. So now, because we're dealing with a data set with about 3 million data points, we're going to actually go ahead and just take a sample from each of these, just to keep the math a little bit more simple. So let's define our sample size as 100, and then we'll say sample race factor, and we'll make that an empty dictionary. And we'll go ahead and type in the first couple of these, and then we'll just go ahead and copy and paste in the rest of it so we're not taking too much time. Again, you can get all of this from our GitHub. So we'll say white sample, colon, random.sample, full race factor, white sample size. And that will give us a random sample of 100 data points from that list. And then we'll go ahead and copy and paste everything else in, add a comma right there, and then make some more make some more space at the bottom. Then we'll go ahead and define our alpha as equaling 0.05. And then we can start doing our other tests. So we'll go ahead and do the ANOVA. This is the same as last time. P, F, significance, DF between, DF within is equal to Oneway ANOVA with our factor and our alpha. And then we'll say if our Oneway ANOVA is significant, we'll continue, we'll go ahead and do a print statement. This is the same as our last video where we did our Oneway ANOVA. So go ahead and just paste that in. There's a statistically significant difference between group means as determined by Oneway ANOVA with our DF, F, DF between, DF within, our F equals such and such, our P equals such and such. And now, if it is significant, we will do a Tukeys HSD. So we'll say the results of Tukeys HSD are, and then we'll loop through the significant queues dictionary. Then we will go ahead and print out the name, the Q value, and the P value for each of our significant Qs. And then lastly, we'll put in a quick print statement if our results are not significant. And this is exactly the same as our Oneway ANOVA and pretty close to the same as our other statistical stats we've gone over. We'll go ahead and save and run. Note, if you're running this takes a little while to run. We're crunching through a lot of numbers. Fix a quick typo and run again. So even with Tukeys HSD accounting for Family error, it's really important to note that it doesn't perfectly solve it. So we'll see here. So more or less all of these at a population level are going to be statistically significant. If we look through this, we'll see we only got 2 that were significant. We'll run it again. We'll see we'll get different results. And it's important to note that this is also a function of statistical power. So how likely are you to get a accurate result based off of the sample size you're using? With something as variable as race, that's actually going to have to be a pretty big sample. 100's just too small. So we'll go and run this one more time. We saw that we got a whole bunch of different ones, and we will probably get different ones again. So yeah, different ones again. And we see that 100 is really just not the right size. And in all actuality, this is a good example for showing things, but it's not a good example for how we want to do studies in real life. This is just a mathematical example using a data set that's available to us. Further down the line in the statistics series, we'll be able to apply better tools, but for now, we're just showing you how this works. Thank you for watching. If you have any questions or comments, leave them down below. I'd love to hear from you about what you think about this series. Don't forget to like and subscribe.